All right, so far we have talked about carbon dioxide and methane, looking at carbon cycles. Now we're going to move on to clouds and aerosols, which for a climate scientist can be pretty infuriating. Clouds are notoriously difficult to model. So they are the hugest, or not the hugest, they are one of the largest sources of uncertainty in our understanding of the climate system. And that's because for a few reasons, but one is they just get in the way of observations. So we make observations either from a satellite looking down towards the Earth, in which clouds are going to cover areas that we want to see, or on the ground looking up into the atmosphere, where again, clouds are going to get in the way of what we can see. So clouds have issues for detection and calculating of different radiative effects. Now, what we do know is that clouds affect Earth's radiative budget. And it affects it in a couple of different ways. We know that clouds, because they're white, they reflect incoming solar radiation, so they have a high albedo, which could cool the planet. But also water vapor is a greenhouse gas. So just like carbon dioxide, just like methane, it's trapping radiation that does make it all the way to Earth. So we've got this albedo effect and this greenhouse gas effect kind of fighting. And overall, if you take the average of all the clouds on Earth, we do think there is a net cooling effect because the albedo is stronger than the effect of the greenhouse gases. But it's not that simple because it's not that every cloud doesn't operate the same. It depends on where the cloud is in the atmosphere and just the general structure of the cloud. So high clouds in the atmosphere, they tend to allow more incoming solar radiation to reach Earth. And they have a pretty strong heat trapping ability as a greenhouse gas. That means that clouds that are high in the atmosphere are going to trap more heat and they're going to cause a net warming impact. Low clouds, on the other hand, they are going to reflect more sunlight and they tend to trap less heat. So low clouds are what have that overall net cooling effect, which means that if clouds change their position in the atmosphere in the future, if clouds become higher in the atmosphere, they could actually become a heat source. But there's uncertainties around this, right? We're not quite sure exactly how clouds are going to behave in the future. So low cloud amount over the Arctic Ocean varies inversely with sea ice amount. This just means that the more open water there is, the more clouds are produced because the more evaporation there is. So thinking about everything that we've learned and trying to apply it to the Arctic, what type of feedback might this relationship produce? Okay. You might first think, well, if clouds have a net cooling impact and the less sea ice there is, the more clouds there are, then that's a negative feedback loop, right? Because the sea ice melts because of warming, this produces more clouds, those clouds cause cooling, that reduces the warming. But again, clouds are hard to predict and they behave differently depending on where they're at. So this is a demonstration of just how dynamic clouds are, where your first idea might be that this is a negative feedback loop. It's actually not so simple. And that's because Arctic clouds, despite their low altitude, have a net heating effect at the surface because their downward emission of infrared long wave radiation, that's the radiation coming, going up from the Earth over the year, outweighs their reflection of sunlight coming down during the short summer season, right? So again, we talk about how clouds have this competing effect of albedo versus greenhouse gas. Well, in the Arctic, near the poles, right, there's times of the year where there's just no sunlight. So it doesn't matter how white something is. If there's no sunlight coming in on it, it's not going to have a strong albedo effect. And this is what we see in the Arctic. Now, might this change in the future? Possibly, right? Things are changing in the future. But again, clouds are hard to predict and they're hard to model.